Terrestrial network, and which are still the challenges that need to be addressed in these systems. So let me first acknowledge the support of my colleagues from the Digital Research Group here at the Università of Bologna, Alessandro Guidotti, Carla Matetti, Bruno De Filippo, and Riccardo Campana, who actually helped me with the slides and all the details in the presentation. The structure of my presentation is as follows: a brief introduction, giving the rationale of the NTN, and a quick note on the evolution from SATCOM to NTN. Then a few slides on the basics of the principle of satellite communications, in particular orbit constellation terminology, so as to align and be able to use then a few of those elements in the second part of the talk. Then I'll go to the SATCOM challenge, which actually are the same and have been the same for many years now: link budget, Doppler delay, and constellation. And then we'll actually dive into the non-terrestrial network seen from the 3GPP standards, 3GPP forum, the architecture, frequency ranges, and services, and then the challenges in this NTN part. So essentially, as you will see, GNSS free operation, the plexing, NTN-based positioning, and so on. And then just one slide on IRIS², just to put in the frame also the activity that at the European level is being developed on this governmental and institutional activity, and then the conclusion. So let me go to the introduction pretty quickly. At the last Mobile World Congress, there was presented the GSMA intelligence report that actually stated that 60% of current cellular worldwide users are ready to pay up to 5% increase to have NTN connectivity of their smartphone. This is not just to have a specific service, but is to have a NTN phone ready to connect to NTN, to a satellite system whenever it's necessary, being that the case of service continuity or emergency situation, or simple to send a message from a remote area to family saying, I'm okay. And this is actually a huge market that can be actually still untapped by the system. So I'm not talking about, and this is not about broadband connectivity, it's not about internet at home, it's just to have a connectivity on the smartphone, on the handheld. At the same time, the same report actually showed that besides the consumer market, there was also the enterprise market, the governmental market, which actually sum up to more than $30 billion in the next 10 years, just as a revenue from the NTN system. And this clearly pushed towards the use and towards the development of NTN system fully integrated in 5G and 6G. Last March, 10 to 11 in Incheon, Seoul, South Korea, 3GPP actually held the 6G, what it was called the 6G workshop. Now, at this workshop, there was more than 1,800 attendees, 750 in person, 230 contribution, very quick contribution, clearly. But out of those contributions, in the 75% of those, NTN was actually listed as one of the key elements for 6G. The other big topic was AI, which was in 78% of the contribution. So all in all, NTN was actually shown as second only to AI, and right after it in this huge event for 3GPP. So this actually tells us that NTN will be a structural element of future 5G, 6G communication. There's the market, there are the technological enabler, the standardization enabler are put in place. 3GPP is working on that. We are sure that 5G and 6G will actually foresee an NTN component fully integrated or fully unified with the terrestrial one. So let me go a little bit onto the detail of what I we saw in the past, the path that brought us to NTN. We know that it has been satellite communication for many decades. And when we thought satellite communication, we say essentially the use of artificial satellite to provide communication links between various points on Earth. But in the past, this satellite communication was totally separated from the terrestrial cellular system. So at a certain point, non-terrestrial network entered the scene, and entered the scene in the acception, in the meaning of use of space and airborne platforms organized in a connected infrastructure to provide wireless services on Earth, not just a general service, wireless service totally integrated with a cellular system. So although NTN nowadays is used by us academics to indicate a wide general concept of communication systems that are not terrestrial but are above the Earth or under the water, the term non-terrestrial network was initially introduced in the context of 3GPP, new radio standardization, and is nowadays totally and fully considered as a 3GPP term in order to address the satellite part, the flying part of 5G and 6G ecosystem. So to go into a little bit into the details of satellite communication fundamental, let me just go and bear with me with the very basic, but I believe it's very important to understand NTN. So a satellite is essentially an object that not flies, but orbits around the Earth, in this case, according to the 3 Keplerian laws. And this is very important because these 3 Keplerian laws tells us that, first of all, the trajectory of the satellite is an ellipsis or a circle in specific case. That there's the second law tells us that equal areas are spanned by a satellite in equal time. So the farther you are from the foci of the ellipsis, the faster the satellite, so the slower is the satellite, the closer to the foci of the ellipsis is the satellite, the lower it is. And the third law is very important because it tells us that the period of the orbit is proportional to the cube of the semi-major axis of the ellipsis or of the radius of the orbit, which actually tells us that the closer to the Earth, the faster is the satellite, according to a precise law. So in satellite communication, the Earth is in one of the 2 foci of the ellipsis, and the satellite actually orbits around the Earth. Most of the orbits that we are considering, that we will consider in the next slides, but we are considering NTN, are actually circular orbits. So the 2 foci actually coincide, and the Earth is at the center of the orbit. The satellite that we are considering consists of 2 parts. One is the platform itself, so it's essentially the part that flies, and the other one is the payload, so what is actually carried by the satellite. And in our terminology, we identify a communication satellite as a satellite carrying a telecommunication payload. This is very important because out there in the space, there's not just satellite communication. There are Earth observation satellite, navigation satellite, there are scientific mission satellites, and a lot of research dedicated satellites. So it's pretty crowded in the space around the Earth. And we see that, and we will see that this can actually be quite a problem in the future to come. So in terms of terminology, we use the terminology orbital plane to describe the plane in which the orbit of the satellite actually lays. The sub-satellite point is the point on Earth's surface direct below the satellite. The elevation angle, which is a very important parameter, is actually the angle between the local horizon plane on which the user of the terminal is and the satellite direction. So a 0 elevation angle means that the satellite is down to the horizon. 90-degree angle means that the horizon is just on the vertical of the user. This is very important because according to the elevation angle, so for varying elevation angle, the distance of the satellite from the Earth or from the user changes a lot, and this is the slant range. So the slant range is a function of the elevation angle. Even if we say that a satellite is flying at 500 kilometers of altitude, the slant range, so the distance between the user and the satellite, depends on the position, on the elevation angle under which the user sees the satellite. And this has an impact both in time, in delay, in Doppler, and in attenuation. And the field of view is actually the angular coverage of the Earth as seen from the satellite. And we will see that the lower the satellite, the smaller is the field of view. Now, having said that, another important element that we need to know is that since the orbit of a satellite actually is a solution of the Keplerian equation, we just need the 6th element to describe the position of a satellite around the Earth. And I'm not going into the 6 elements, but it's very important to understand this because these 6 elements in NTN are transmitted from the satellite to all the user in order to tell the user where the satellite is in its orbit. And this is actually transmitted in the famous SIB19 table broadcasted by the satellite to the user in coverage. And this, as we will see, is very important because it helps us to define the relative position between the user and the satellite, and thus to pre-compensate Doppler and delay. We will see this in the future slides. Now, the last, essentially one of the last slides about satellite fundamental is the definition of the orbit. We use terminology like geostationary or orbit geo for those satellites that actually rotate with a period which is equal to the rotational period of the Earth and are seen as a fixed point in the sky by a user on the ground. There is just one solution to the Keplerian equation in order to provide this condition, and this solution places the satellite on a circular orbit where the orbit actually lays on the equatorial plane, so the sub-satellite point of the satellite is just on the equator, and the distance from the Earth is this 35,700 something kilometers. So this is the only orbit where the satellite can be seen as a fixed point on the Earth. In any other orbit, higher or lower, the satellite moves with respect to a fixed point on the Earth. And in particular, we have the high elliptical orbits that were used by the first communication systems, and like the Molniya orbits that have an apogee at 40,000 kilometers of altitude and the perigee of 500 kilometers of altitude and a period of 12 hours. So essentially, the satellite design an enit on the surface of the Earth and can actually cover a region of the Earth. Then we have a medium Earth orbit satellite, which are circular orbits with period in the order of several hours, 6 or 12 hours, and an altitude that goes from 8,000 to 20,000, 22,000 kilometers. These are very important orbits because of the orbits used by the GNSS satellites, so by Galileo and GPS, for example. And then we have the low Earth orbits, LEO, which are very popular today, are circular orbits with a period in the order of few hours and an altitude that actually span from 500 kilometers to 1,500 kilometers. And below that, we have the very low altitude orbits, the VLEO. These are circular orbits with a period in the order of less than 2 hours and an altitude between 200 and 500 kilometers, typically 300, 350. These are specific orbits because below the 500, you are already into the atmosphere. So while a satellite actually, you can think of a satellite as a in low orbits, medium, high, or geostationary orbits as a device which actually has nothing to do with the flying, so has nothing to do with the laws of drags and lift that actually are related to flying into the atmosphere. Satellite below 500 kilometers start to be some elements that are flying in the atmosphere. So while satellite above 500 kilometers have no wings, in the low Earth orbits, the form factor of the satellite has to change and become something which is more similar to an airplane or something with wings, because there is the drag and lift of the atmosphere itself. These orbits are also very interesting because being into the atmosphere, they offer a protection to the cosmic ray. And so they offer a protection to the device on board of the satellite, which then can be, let's say, consumer-like elements, electronics, and not necessary hardened components as it has to be for the low Earth, medium, or geostationary orbits. And this actually opened quite a market for small and medium enterprises who are willing to enter the market itself. Besides this, what we call spaceborne, there is also the airborne platform, which are not treated in this talk, high altitude platforms and low altitude platforms. I'm not discussing those because in 3GPP, essentially apps and labs are considered as a very low stationary platform, so not moved with respect to a fixed point on Earth, so no Doppler, low delay, and a very nice link budget, and the low round trip delay. So in 3GPP, when we go to airborne, we assume essentially a geostationary satellite with a super nice link budget, low latency, and no Doppler. So having said that, we can actually think of a satellite communication system like a space segment where we have the elements flying, so the satellite flying connected by inter-satellite links. The control segment, which is actually the part on Earth that actually control the infrastructure, so the flying of the satellite and allocates power and bandwidth and everything else to the different nodes in space. And then we have the ground segment, which actually consists of the gateway, which is the access point to the core network, essentially, or to the network itself, and the user terminals, which are connected to the satellite through the user link. And the user terminals can be handheld, rooftop antennas, mobiles, and so on. Okay, on the basis of this, we can actually start thinking of what are the SATCOM challenges, the challenges that have been addressed by NTN. So first of all, attenuation and delay. If we look at the attenuation of the GEO satellite, just considering the free space loss at two frequencies like 2 gigahertz and 30 gigahertz, which I've not selected randomly, but they are actually the two frequencies on which the NTN is working right now. So FR1 and FR2, little below 2 gigahertz for the S band, a little below 30 gigahertz for the Ka band. A GEO satellite has essentially an attenuation in the order of 190 to 113 dB. A MEO goes down to 200 something, but if you go down to LEO, to a very low LEO, so 500 kilometers or a VLEO, you see that you gain something like 40, 50 dB in attenuation. So you reduce the attenuation by in the order of 40, 50 dB, which is a lot and which allows to have a nice link budget. On the other part, if you go down and if you go from GEO to LEO to VLEO, you see that also the single link delay, essentially the delay that takes the electromagnetic signal to travel from the user to the satellite or the other way around, goes down from 125 milliseconds single link to 1 millisecond, opening therefore low latency the system to low latency application. Now, so the ideal thing is to go from a GEO satellite to a LEO or VLEO. For many years, we actually had system using GEO satellite to provide digital broadcasting television or broadband internet access based on GEO satellite. Going to LEO, the link budget improves, as we said, the delay improves, but actually something happened, and is that the field of view essentially reduces. So if we can stay for a moment on the link budget, a simple formulation of the link budget tells us that the C over naught, so the power of the carrier divided by the power spectral density of the noise, depends essentially on the IRP, on the G over T, which is characteristic of the receiver terminal, on 1 over L, which is actually depends on the attenuation, is the free space attenuation plus other attenuation, but the main component is the free space loss, and then is 1 over K, where K is the Boltzmann constant. So essentially, if we look at the C over N0, or if you look at the right on the ES over N0 times the data rate, we actually looking at the performance of our telecommunication system. The ES over N0 is what control our spectral efficiency, and the data rate is what we actually would like to provide. So given the C over N0, we can actually trade ES over N0 with data rate. So we can actually have low data rate services with high ES over N0, or high data rate services with lower ES over N0, therefore with lower spectral efficiency, just following the classical Shannon capacity formula. Having said that, I'm just saying we need, in any case, for satellite communication and NTN, the clear point is to improve the link budget. So in order to improve the link budget, we can actually go and look at the link budget equation and say, okay, we can increase the ERP. How do we do? We can increase the transmit power, or we can increase the antenna gain. So suppose to look at the downlink for the moment being, everything is reciprocal. If we increase the transmitted power, we need to have more power on board of the satellite. We need to have essentially more battery or larger solar panel in order to produce DC power to be transmitted on the RF front end, which actually tends to tell us that we need a larger platform. And this is clearly demonstrated by the trends. You know pretty well that there are US companies launching satellite with a surface of 64 or 100 or more than 100 square meters antenna, and on top of the antenna, solar panel, in order to have a nice ERP. Because the other element that can increase the ERP is the antenna gain. But whatever we do with antenna gain, the antenna gain is somehow related to the dimension, to the surface of the antenna. So in order to increase the antenna gain, we need to enlarge our antenna, or to have more elements in whatever antenna, array antenna we have, which tends to tell us that we need to fly larger platform. And flying larger platform means to a larger cost, because we need to launch the satellite, we need to build that, and so it's essentially a larger cost. On the other side, we can actually increase the C over N0 by increasing the G over T, where T is the noise figure, the equivalent noise temperature of the receiver. Assuming that we have done a good design of the receiver so that T is fixed, we need, to increase the G over T, we need to increase the receiver antenna gain. And this actually tells us that we need to go for larger terminals. So if we want to communicate with the handheld, we have no chance to increase the G of the antenna. Yes, there are initiatives, there are studies and design of nice antennas within the terminal that create a nice lobe towards the satellite, but at the same time, this is not a super directive antenna. It's a somehow directive antenna, but the G is not as large as possible, or as large as you can have on a rooftop antenna, classical dish, 60 centimeters diameter, or a squared antenna like those of some famous service provider that are 60 by 60 centimeters, 57 by 57, something like that. So they increase the G over T by increasing G is an option only on some platform, which are actually the platforms that are not anchored. So the only other element that we have is to reduce L. And to reduce L, we need to reduce the distance between the transmitter and the receiver. So we need to go from GEO satellite to LEO to VLEO satellite. But in doing that, what is happening is that the field of view of the satellite actually reduces. On the left here, you see the field of view. So the point of the Earth seen by the satellite for a GEO satellite, and you see what a LEO satellite actually sees in terms of surface of the Earth. So if we go a little bit more in detail on this one, and we look at the constellation and essentially at this table that actually reports for the different orbits, the Earth coverage in percentage at 2 elevation angles and the visibility time of the satellite at 2 elevation angle, you see what is happening by going from GEO to LEO. A LEO satellite with 0 degree elevation angle, so assuming that you can actually link to a satellite which is a 0 degree on your horizon, you have 42% of the surface. And then you go down for a LEO at 500 kilometers to 3.6% or even 2.2% of the Earth in terms of visibility of coverage. But if you start increasing the elevation angle and you go to 40 degrees elevation angle, then this number reduces a lot. And for a LEO at 500 kilometers, you go down to less than 1% of the Earth and less than 0.7% of the Earth for a VLEO. Now, the 40 degrees elevation angle is not a number so large, because when you go to situation where you can actually have obstacles on the horizon, so obstacles that actually interrupt the visibility from the satellite to the user, you want to use a higher elevation angle in order to avoid those obstacles. And at the same time, we will see in the next slide that by using a 0 degree elevation angle, you increase a lot the difference in the slant range from the from the user that are at the border of the coverage and the user that are on the other side of the coverage, which actually introduce differential Doppler and differential delay. So the 40 degrees angle is something which is actually reasonable and is being used. And you see that for this, not only the Earth coverage reduces, but also the visibility time of a satellite reduces a lot. For a 40 degrees elevation angle, we have for a LEO, a visibility time of 5 minutes that goes down to a VLEO for 1.5 minutes. So this is actually a very challenging number, because in this time, you need to do the synchronization procedure, if you need the estimation procedure, and link and attach to your satellite and do your transmission. So you see that even going to LEO or VLEO is very important, very productive in terms of attenuation and delay. On the other side, we lose in visibility and we lose in coverage, which actually tells us that we need to increase the number of satellites to have a full coverage of the Earth. And we need also to increase the number of satellites in order to have a continuity of the services. So we have essentially two elements here: global coverage, which can be reached with a number of satellites, and service continuity in time, which actually ask for even more satellite. So just to give you an example, you can actually reach a geographical total coverage with the 24 satellite at an altitude of, let's say, 500 or 600 kilometers, but you need hundreds and hundreds of satellites in order to obtain not only global coverage, but also service continuity. So what I'm actually saying is that the push towards LEO and VLEO actually is a engineering trade-off design between cost of the constellation and coverage, and also telecommunication challenges related to the fact that the satellite is very fast, there's a high Doppler, and there's also a very limited visibility time. So wrong direction. So if we look at the delay and the Doppler, we see that by reducing the altitude, we reduce the propagation delay, but we increase the Doppler. The third law, Keplerian law, tells us that by reducing the altitude, we increase the speed of the satellite. So on the left here, you see the one-way delay according to the elevation angle from 45 to 90 degrees. You see that there is a variation in the one-way delay in milliseconds, even for a LEO at 600 kilometers of altitude, because of the different elevation angle. But if you look at the Doppler as well, you see here essentially the variation according to the path. You see that the Doppler for the LEO varies quite a lot, also in terms of elevation angle. You have to assume here that 0 means that you start seeing the satellite, and 180 you lose the satellite. So you see the variation, which means that user in the coverage area experience at the same time different Doppler and different delay. And this is what we call differential Doppler and differential delay. Again, user in the same coverage actually experience, notwithstanding their own speed, differential Doppler and differential delay because of the different elevation angle they see the satellite, and therefore the slant range they actually experience with the satellite itself. So now coming in non-terrestrial network. So on top of this, we built essentially non-terrestrial network. So the non-terrestrial network is not something that has been actually built overnight, as we used to say. The first introduction into 3GPP of non-terrestrial network started with release 15, essentially. I guess that you are aware of the fact that 3GPP works according to a work plan that actually consists of study item and work item organized in time. A study item is a study phase that actually produces a technical report. The technical report is not a normative document. It's a document where different technical solutions and challenges are actually addressed and described. Out of the study item, it is possible that 3GPP decide to go for a normative phase where a work item is initiated and the specification for a particular feature of a particular system are actually defined. And this work item actually produce a technical specification, so actually a standard. So release 15 and release 16 of 3GPP address the study phase for NTN in terms of all the challenges, architecture, channel model impairment, and so on. Now, the normative phase started only in 2020 with release 17 and was completed in March 2022. And that normative phase produced release 17, where the enablers to use NTN into the 5G NR 5G architecture, in particular for the 5G NR radio interfaces, have been defined. And that, as we will see in a while, that specific standard foresees the use of transparent payload, geostationary and non-geostationary satellite, and only S and L band in FDD, which means FR1. So only the frequency that we have identified as below 2 gigahertz. FR1 is below 10, but in any case for satellite, for NTN, it's just below 2 gigahertz. So bandwidth, we'll see the bandwidth 1.6 and 1.9 gigahertz. Then following release 17, in 5G Advanced, release 18 and current release 19 are still addressing satellite communication, and in particular, they're addressing different aspect, not only smartphone in S-band, but also fixed VSAT terminals, so small aperture satellite for an NGSO, sorry, small aperture terminal, so terminals with terminal with the antennas with better gain for fixed and mobile system, and also not only in S-band, but also in FR2, so in Ka band, a little below 30 gigahertz. And in release 19, not only the transparent architecture are addressed, but also the regenerative one, and also what is called the UE SAT UE, which is mesh connectivity. So essentially, as we will see, the connectivity that actually goes only on the satellite and down again to a terminal without going down to the gateway itself. And then we have release 20 and release 21, where 6G will actually be addressed with multi-layered autonomous constellation, smart routing in space, our interface adaptation, and we don't know what will be actually into the system itself, but I have a list of potential development at the end of the tutorial. In NTN, so if you look at NTN now, at the very beginning, two main services category were actually considered. The first one was what was called indirect connectivity, where the satellite is connected to an Earth station and the user terminal are connected to the Earth station through the so-called 5G and RUU, so with the 5G radio interface. This is essentially very similar to a backhauling architecture. The other very interesting and much more interesting connectivity is what we call direct connectivity, where the satellite direct connects terminals on the ground through the 5G NRUU. So as you see here in the second figure, essentially the satellite with or without a regenerative payload transmit on the user link the NRUU. In the first scheme, it's not necessary to transmit the NRUU interface on the user link of the satellite. It could be other satellite radio interfaces carrying the 5G NRUU. So coming to the direct connectivity, which is the most interesting one, we can split again in two main categories. One is the direct to handheld or direct-to-device communication, in which we have smartphone-like terminals. In this situation, we have a terminal which has a smaller antenna. It's clearly in low frequencies, like FR1, so essentially S-band, which has a very nice propagation characteristic, does not require, in that range, we are not required to have a very directional antenna. Atmospheric attenuation are not so impactful as in Ka band. And this is actually the type of connectivity that is used to give service continuity. So, and probably, and also emergency services. So it's actually service continuity in normal business as usual operation, where you actually have a phone call or a video call or audio call on your mobile phone. You get out from the terrestrial connectivity and you get actually hand over to the NTN and back to NTN when you re-enter the terrestrial connectivity. This is a pure service continuity in geographical and time perspective. It's not really enhanced mobile broadband. It's a broadband in the sense that is communication to a smartphone for this type of services. The other big category is actually direct to fixed or moving terminal, which are larger platforms like home and building terminal with a rooftop antenna, mobile platform terminal like car, train, boat, etc. Well, you can actually put a flat antenna or an array with quite a large gain, so a larger antenna, you can actually use high frequency band that actually requires directivity of your antenna, like FR2. So you have a better link budget and you can have a higher data rate. So if you look at the two categories, it's pretty interesting to see that in the lower frequency bands, we are actually having smaller antennas, more constrained link budget, but we do not really want super high data rate. Whereas in the second case, we have a better link budget. Usually we have better or larger spectrum chunk at higher frequency. So we have a better spectral efficiency from Shannon. We have a better bandwidth, so we have a better capacity and then higher data rate. And then is where actually you want to have a internet-like or broadband connectivity. Essentially, this second part is where other constellation and services not based on 5G or advanced 5G are currently offering services all around the world with mega constellation of thousands and thousands or low Earth orbit satellite. Wrong direction. So in terms of, no, correct direction. In terms of direct access, two main architecture have been addressed in NTN. One is the transparent payload. In this case, when we say transparent payload, we do not say that there's no onboard processing. There's a lot on onboard processing, routing, commuting, beamforming, analog or digital beamforming. We are actually considering transparent payload in the sense that run function and protocols are not implemented on board. So the access straight to protocols are actually terminated on ground and not on the satellite. So there's no essentially G0B implemented on board, even if you have a lot of processing on board, or you can have a lot of processing on board. On the other side, we have regenerative payloads that are addressed in release 19 that were not addressed in release 17 and release 18, that might have some or all the run function implemented on board. So you essentially can have a full G0B on board, or what we can call as a distributed unit in the sense of functional split, 3GPP functional split on board, whereas the centralized unit can be on ground or on different satellite. And that is something that we will show in a few minutes on what we call a distributed architecture for 6G. So it's not really implemented, not really foreseen in 3GPP, but distributed architecture are actually foreseen and as a smart way to design constellations that are sustainable. So coming to release 617, a quick, just one slide on release 617. Release 17 was based on GEO and LEO satellite apps and drones and so on. As I said, implicitly considered as GEO with a very nice link budget. The main characteristic, transparent payload architecture, earth fixed or quasi-earth fixed or earth moving beams. Essentially, the antenna on the satellite can actually be steered in order to keep the beam, the focus on a specific area, or not steered so that the beam moves with the satellite. Only FR1, so S-band, as you see here, 1.9, 1.6, and 1.9 gigahertz or 2 gigahertz of carrier frequency. Handheld only terminals with GNSS capabilities, and we'll be back on the GNSS capability right now. Only FDD, frequency division duplexing, and the introduction, and that was the new part of the SIB19, which actually contains the information of the satellite position in its orbit. Now, this is a very important point. If we consider the initial acquisition phase of a terminal that want to attach to the network, you have seen that there are a few elements that need to be compensated. One is the Doppler and one is the delay. User on ground which are not co-located, experience different Doppler and different delay. 5G NR is based on FDN, we know that, so on a frequency time grid. So essentially the delay produces a misalignment of users that actually reach the satellite at different time, whereas the differential Doppler produce a shift in the frequency grid that makes the user not to be orthogonal when they reach the satellite. So in order to compensate this differential Doppler and differential delay and allow and enabling the time frequency grid of the user on ground to reach the satellite aligned in time and frequency, the user has to pre-compensate its own Doppler and its own delay. And this is pretty straightforward because the user, before sending the rack message, so before attaching to the network, is unknown to the network itself. So there's no way that the network can pre-compensate for the users on ground. The network can at most pre-compensate a common Doppler and delay, maybe the center of the beam, but cannot compensate the differential Doppler, differential delay that you have seen are actually experienced by user separated within the coverage area of the satellite. So what has been introduced in release 17 is the SIB19. The SIB19 tells the user where the satellite is. Now, the user can actually compute its own Doppler and its own delay by knowing its own position. But then the user can only compute its own position right now by having a GNSS on board. And this is actually a common experience. All the smartphones that we have GNSS, Galileo, or GPS on board. So the user can actually compute its own position, knows the position of the satellite, knows the speed of the satellite, knows its own speed through GNSS, and can pre-compensate its own Doppler and its own delay in order to reach the satellite aligned to all the other users. This is actually the pre-compensation that is actually introduced by the terminal, by the UE, thanks to this SIB19 and to the assumption of GNSS capabilities. And this is actually the key point, one of the principal elements introduced in 3GPP to allow NTN to operate with the 5G NR. Now, if we go to release 18, release 18 actually introduced the use of FR2, sorry. You can see here N511 and 510, which is actually in Ka band, actually communication in Ka and Ku band for the downlink, always in FDD. Then in release 18, also the network verification based on the GNSS has been introduced. So essentially the terminal compute its own position and communicate its own position to the network in order to be verified. And this is for authorization use of specific network in specific area of the globe. A mobility procedure has been introduced and coverage enhancement, so techniques allowing to improve the coverage for the uplink have been also introduced. But the key point for release 18 was the introduction of FR2. So which are the open challenges in this context that NTN has to address beside what is already in the specification? Let me go on a list of what we see as open challenges. First of all, we need to have a fully regenerative or part of the G-Node-B on board. This is under study right now, but still it's a challenge. It's a challenge because we need computational power on board of the satellite, and we need to introduce all those elements that allow a G-Node-B to hand over with respect to the core network, which is on ground. So the regenerative payload on board is still a challenge and is being addressed by release 19 for the moment being. The store and forward capabilities. There are situations in which the satellite needs to store the information received by the UE and then forward on a subsequent time. So the case where a satellite is flying, it has no inter-satellite link, so it cannot connect to any other satellite, and there's no feeder link, so has no gateway invisibility. This is a classical case of store and forward, emergent communication. For example, you want to send an SMS, you are lost in some mountains, you send an SMS, the satellite actually stores your SMS and delivers your SMS a few minutes later, 30 minutes later, 14 minutes later, telling the position of the person lost on the mountains or the message that the person wants to deliver and so on. And again, the store and forward is something which is actually addressed in release 19. UE, SAT UE communication, as I said, mesh communication. So you see a picture here of a UE communicating to another UE under the same coverage of the satellite without going down to the gateway. These are classical situations for emergency case where for example, the terrestrial network could be down because of an electricity failure, like what happened in Spain a few weeks ago, or a flooding or whatever else. So you want to be able to connect two users under the same coverage without going down to the gateway. And this is what is called UE, SAT UE communication, and this has been addressed in the current release 19 work. Then an important point is this GNSS resilient or GNSS free operation. This is a super hot topic, very interesting from the communication theory perspective. So as I said, right now, the user can actually attach to the network by knowing the position of the satellite and by knowing its own position. And its own position is actually computed through GNSS. But although all the terminals have availability of GNSS, there are regions in the world where GNSS is denied or where GNSS is not available for some reason, could not be available from some reason. Those regions are exactly the region where you want to have a communication system that does not rely on terrestrial network, but relies only on satellite communication. And if in those cases you cannot connect to the network because you're not able to compute your position, then the added value of the NTN component is lost. So what is under study right now as a GNSS resilient and will be studied in release 20 and 21 as GNSS-free operation is the synchronization of the user to the network without the assumption on knowing the position of the user. This actually requires new signal format in order to ensure the orthogonality also in absence of Doppler and delay precompensation, new estimation algorithm at the G node B in order to be able to tackle the residual Doppler and delay. And what else? It's still a big question mark. Here, the subject is totally open to solution and to research activity. Then we have low SNR operation, which actually are very interesting for indoor communication for emergency services. This is actually a request that comes from the mobile network operator to have the ability to send short messaging, short voice messaging to a user within indoor, maybe just the first wall, in order to be able to serve those users in case of emergency, an earthquake, flooding again, and so on. So operation in very low SNR, which can call for new codes or extended forward error correction, new repetition code, different techniques, better link budget, and so on. So essentially, we need to gain 20 dB of first wall penetration given or taken. Then TDD duplexing, in order to use also those frequencies that will not be paired, so not only FDD, but also TDD. TDD is really inefficient for satellite right now, because the guard time should actually be linked to the maximum propagation delay that becomes very large in terms of, with respect to the payload of the message. So TDD duplex is under study. A routing in space with a constellation of thousands of satellites and satellite link one each other by inter-satellite link. We need to go and we need to improve the way in which we can route signal in space. And last but not least is a design of multi-layered heterogeneous constellation, which are smarter and more sustainable. I just want to spend 3 slides on this, and then I'm done. So just 5 minutes more. The constellation design, the infrastructure design is a very important element. So what I'm now showing is the result of a project that I'm coordinating. It's called the 6G NTN project. And we designed a concept of a new architecture, a new constellation, in order to try to address the problem that mega constellations are actually posing to NTN. Let me just go into the limits of mega constellation, at least some of the limits: technical, economical, and environmental limits of challenges. Technical, if you start packing the space with the thousands and thousands of satellites, the antenna resolution capability of a terminal becomes too low and insufficient in order to discriminate between the interference. And you need to go with a very sophisticated spectrum coordination and coexistence, which at a certain point will actually be not enough to address the problem of interference created by the thousands of satellites flying to the terminal. Going towards thousands and thousands of satellites are actually posing a burden on the production capability, the continuous production capability, and on the launching capability. Clearly, we have solutions right now, but those solutions actually depends on just one single launching system, which is mainly US-based. So there are technical challenges and many more in going for thousands and thousands of satellites. On the other side, there is also economical challenges. The launching cost, indeed, even if you have a very smart and very nice launcher, if you launch 10,000, 20,000 satellites, this is going to cost. The infrastructure, the flying infrastructure cost and management is very high. So becomes really a burden to the satellite network operator to deal with that super huge constellation. And then we have space crowding. Sooner or later, we will reach a situation where the space will be so crowded there will be no place for others. The space, as the CTO of Viasat actually introduced in a conference, in SMS conference, is a common. So as a common needs to be approached, economically speaking, like a common resource, not just a shared one. A common resource need to be addressed in a common way. And then there are the environmental challenge, which is the environmental footprint of producing all these satellites and launching all these satellites and having the debris in production in orbit due to the degradation of the satellite. And last but not least, this Kessler effect that was actually studied by another researcher many years ago, and that we are now approaching. If you put a lot of satellites, one close to each other, what we are risking is at a certain point to have a chain effect in the destruction of a satellite. So the satellite will be so close and so packed one each other, then when a debris hits one satellite and this actually goes and explodes and produce other debris, this will actually initiate a reaction chain, which is called a Kessler effect that is foreseen as to produce an unusability of that specific orbit for decades in order to be able to clean that orbit from the debris produced by this effect. So indeed, we need to go towards smarter way of designing constellation. So what we have actually designed, I can skip this one, is a constellation that actually is differentiate from the conventional one. In a conventional constellation, you have all the satellites with the same functionality, in the same orbit, I mean. And all the satellites have user link to connect to the user and feeder link to connect to the link. And then they may have optical inter-satellite link to connect to other satellites, let's say 4 adjacent satellites. And then they can have an RF payload to connect to satellite in different orbits. Usually you go with an optical inter-satellite link to the same orbit and with an RF link to other orbits. And since all the satellites have the same functionality, either you have transparent payload or you have all the run functionalities on board of that specific satellite. Now, a distributed architecture is an heterogeneous architecture with heterogeneous nodes where you have two types essentially of nodes. Feeder nodes that are platform with higher computational capabilities, and service nodes that are platform with lower computational capabilities, smaller platform, lighter one. The feeder nodes have just feeder links, so RF connection to the gateway and no connection to the user link. This is essentially the centralized unit. They have optical inter-satellite link to 4 different service nodes, to the smaller nodes, and they have optical inter-satellite link to 2 different feeder nodes. So you can think of a cluster, a swarm of satellites flying at the same altitude of 5 satellites, 1 feeder and 4 services. The feeder is a larger platform. The service are a smaller platform with lower computational capabilities. The service node have connect to the user. They are the distributed unit. They can use all the power to provide capacity to the user. They have just 1 inter-satellite link optical to the feeder node, and they have also minimum run functionality, the distributed unit or even only the radio unit. So if we go, I'm actually skipping this on the functional split. If we go to this example of architecture, in the project we have dimensioned this architecture with an altitude of 600 kilometers, near polar inclination, so 87 degrees. So it's 90 degrees is the polar, so the satellite crossed the polar. 87 degrees are the inclination of the orbital. 45 minimum user elevation angle to avoid, as I said, obstacle. At least 1 satellite always visible, and at least 10 seconds of overlap between 2 satellites in order to do handover between the 2 satellites. And you see that the number of satellites that we can reach with this type of distributed architecture is very low. 1,600 satellites, not 10,000, not 20,000 satellites. And at the same time, the capacity that we can reach by putting all the power of the service link, of the service terminal to serve the user is actually increase the overall capacity of the system. And these are very flexible architecture in which you can actually trade off power, size, and weight of the different platform in order to optimize the cost of your infrastructure. So what I'm saying here is that we do not need to go to the brute force or launching 10,000 of satellites to have a full coverage of the Earth with 5G and our similar performance. We can actually have very smart, well-designed and thought architecture and reach a better economical, technical, and environmental sustainability. Closing now, what else? You might have heard about IRIS². IRIS² is something which is in the framework of all what I said, but is actually a specific system supported by an European Commission initiative for governmental, institutional, and business users, financed with 6 billion by the European Commission, with 550 billion the European Commission, and then 550 million from ESA, and 4.1 billion from a industrial consortium called SpaceRISE. IRIS² will actually provide services, is actually the third pillar. So you have Galileo, you have Copernicus, the third pillar is IRIS². It's based on 5G NR and 6G, essentially only in Ku and Ka band, so only VSAT terminal, no communication to the handheld for the moment being, and actually consists of 3 different constellations which do not communicate to each other, so it's not a multi-layered one. It's a high LEO constellation of 264 satellites at 1,200 kilometers, 18 satellites in MEO orbits at 8,000 kilometers, and 10 satellites in very low Earth orbit, less than 750 kilometers, for tests and experiments. So this system is being built by this SpaceRISE consortium, and it's totally based on NTN as defined in 3GPP. To conclude, the path towards NTN has been a path of unification. Before release 16, so before 2021, TN and NTN, TN and SATCOM were just interworking. There was no integration at all. With release 17, 18, and 19, we reached what we call integration of TN in NTN. But the point is that in release 17, 18, and 19, the optimization was actually focused on terrestrial network and just with the support, minimum support for a non-terrestrial network, as you have seen. Now, in 6G, so in 6G and beyond, NTN will actually be, as you have seen, a native component of the 3GPP ecosystem, and this call actually for joint terrestrial and non-terrestrial design, optimization, and operation, which actually opened the floor to a lot, really a lot of new research and development areas in the field of TN and NTN unification. And with this, thanks a lot. Almost in 1 hour. Thank you very much for your attention up to now.
Thanks a lot, Alessandro. Great talk, very, very comprehensive and accessible also for people that are not so familiar with these topics. So really, thanks a lot for making it accessible.